Okay, the next problem we're going to look at here is going to be 432, which is the diagram that we see right up here. And in this problem, we want to find the resultant force, okay, that we have here due to the distributed load, the evenly distributed load, and the concentrated load that we have here. So we are just trying to find what is the resultant and where is it located with respect to A and B. All that just means is this line A to B. So we'll kind of reiterate that, but we need to find the resultant of distributed load plus the concentrated load. So I'm going to start by drawing my free body diagram. Okay. Problem 432. Okay. I'm going to put my convention in my upper right-hand corner. Okay. What was that?
I said after that song.
I can, yes. Free body diagram first. Okay. And we are simply going to draw a line from A to B. Okay. To B. Now our applied loads here, we have a concentrated load right here, and that is 5.2 kilonewtons. Okay. And then you're going to notice that we have a distributed load, okay, right here. Now that distributed load, I'm going to kind of put these little vectors there. That distributed load is 1.2 kilonewtons per meter, okay? Now, as we look at our dimensions here, that is distributed over 3 meters, okay? And then from A, it's located 1.5 meters away, okay? So the first thing we need to do is find the equivalent or the resultant of just this little section here. We want to take that distributed load and we want to make it a concentrated load. Okay, so to do that, we're going to use that value of 1.2 kilonewtons per meter. We're going to multiply it by its length. So step number 2 is going to be resultant of distributed load. Now, I'm going to call that R1 because it's really just kind of like the resultant of that little section. So R1 is going to be equal to, earlier in the chapter, let me see here, on page 79, here is how you calculate the distributed load resultant. You'll notice that this is W, like the weight in pounds per foot, or in our case, newtons per meter. Okay, that's W. And then this is the length. So to find the resultant, which would be the equivalent load right here, we're going to take that W times the overall length. The W in our case is the 1.2. Okay, so we know that R is going to be W over length. So we're going to take 1.2 kilonewtons per meter, and we're going to multiply that by the overall length of 3 meters. Okay. So that means we're going to have our, I'm going to call that resultant 1. Resultant 1 is going to be equal to 3 times, yeah, 3.6. And now the meters cancel out here, right? Top to bottom. And this is going to be 3.6 kilonewtons. So it's just a force. Now, if I go back up here, where that's going to be located, I'm going to move this over a little bit. So this was 1.2 kilonewtons per meter. Its location is going to be right in the middle of that distributed load. All right, it's an evenly distributed load. So we can say, okay, we can replace that with 3.6 kilonewtons, but it's going to be located half the distance from one side or the other. So I'm just going to show it being half the distance, 1.5 meters here. Does that make sense? Oh, that's ugly. That's why we have an eraser, Kelly. Let's make it look nice. So from the edge here, this is going to be located 1.5 meters in, and this value here is 1.2 kilonewtons per meter. I think that's better. Does that make sense? Yep. Now what we've done is we've taken that distributed load and we've now put it into what we call an equivalent. Sometimes you'll see this little curly E there. That's an equivalent load. So it just means that we're simplifying it with one concentrated load that's going to have the same net effect on the body. Okay. So now the next thing that we're going to do is we are going to go through that same process. So the next step is going to be, we're going to sum our moments around either A or B. I'm going to say around A equal to, and we're going to find the value in kilonewton meters, right? Force times distance. So we're going to take the offset forces times their perpendicular distances. And once we get that total moment, step number 4 then is going to be, all right, we're going to take that moment and we're going to set it equal to our resultant. Oh, I didn't do the resultant force. Our resultant times, this is going to be an X bar. To get the resultant force, we're simply going to add these two forces together. Okay. So resultant, I'm going to say where my resultant is going to be equal to negative 3.6 kilonewtons minus 5.2 kilonewtons. So my resultant, my overall resultant, just resultant, not resultant 1, is going to be equal to a negative, it looks like 8.8 kilonewtons, right? Now that value is going to go up here. This value is going to go there. And then you'll solve for your X bar. You think you can take it from there, Danny? Does that make sense?
Yep, that makes sense. Thank you.
All right. You're welcome.